here's the scenario. Sensory input, integrate that input, and then come up with an appropriate motor response. So the sensory input of pain in your foot, integration was maybe 1 or 2 synapses, 1 or 2 connections in your spinal cord, and then we had an appropriate motor command, which was flex your leg. Now, what about this sensory input? You're standing in an open field, and there's waist-high grass. In the grass, about 20 yards away from you, you see these 2 eyes, a furry face, and these ears that you recognize as a lion's face staring at you from the grass. Sensory input is a pattern of light hitting the retina. That pattern of light is going to your visual areas. It's getting interpreted, the little edges, the colors, where the eyes are where they're looking. And then you draw on your memories and you recognize it as a lion in the grass staring at you. You remember that a lion is dangerous, it's a carnivore, you're made of meat, your life's in danger. Your emotional system starts to get activated. Now you've got this sensory input, your memory of a lion, the fact that you're in the presence of this lion, your emotional system is activated, your heart beats faster, your blood pressure goes up. What's the appropriate motor response? Run. That's one. Anything else?
Fight.
Fight. Look for a weapon. Anything else?
Freeze.
Freeze. Now, how different are those appropriate motor responses? You've got run, you've got fight, you've got freeze. Okay? What if there was an SUV behind you? Open the door and calmly get inside. So there's a lot of other possible motor commands that could come out. So we still have a behavior. We've got sensory input, we have integration, and we have an appropriate motor output. But there's a lot more synapses. There's a lot more neurons playing roles in that particular behavior, and it's a lot harder to figure out, sort of tease it apart. So what I wanted to do next, sort of at a larger scale, is maybe tease apart a little bit about what neuroscience is telling us about planning of movements. So when you talk to people that teach introductory neuroscience, you're going to say, all right, you're going to teach the visual system, you're going to teach touch, somatosensory, you're going to teach hearing, auditory system, and who wants to do motor system? Everyone puts their hands down because it's the most complex and the least understood of all the systems we have. So it's very difficult. There are some techniques, though, that have been shedding some interesting light upon this, though. So first, let me show you the primary motor areas of the brain. Okay, I think we can zoom in. Here's the back of the brain. So this would be the back of your skull. It's called the occipital lobe. Primary vision, of course, is in the very back of your brain. It makes sense, right? So your eyes are up front, primary visual area is back here. It actually does make sense because there's a relay nucleus in the very middle of your brain that all visual information has to go through. So it's not going that far any further. Right around in the middle here, you see there's all bumps and grooves. There's typically a groove that kind of goes all the way up from top to bottom along the side. And the grooves are called sulci, and the bumps are called gyri. So gyri and sulci. And the gyri that's on the front side of this is the primary motor cortex. The gyri that's sort of to the back of that is primary somatosensory cortex for touch and pain and temperature. How did we figure this out in a human? Well, it was a neurosurgeon that figured it out back in the 1940s and 1950s. Wilder Penfield. If you want to look into Wilder Penfield, fascinating career. He would go in and he had to have a reason to open up someone's skull and start poking around in their brain. He was trying to relieve symptoms that were causing seizures, epilepsy. These people suffered from epilepsy, they had intractable seizures, and he would go in and try to find that part of the brain that was triggering the seizure and cut it out and remove it. So if you had the brain open and you could poke around and try to find where these seizures were being triggered from, then you could cut them out. Now, you're not going to find a seizure if the patient is anesthetized. So these people had to be awake with their brains fully exposed and conscious and responsive. And he would poke around with a little electrode and try to trigger a seizure. Okay, basically. While he was poking around and shocking the brain with little currents of a little bit of electricity, he would write down in a notebook what the patients were experiencing. And he put little stickers on the surface of the brain that had different letters, and every letter had a little response. This person's right arm twitched. The person's right leg twitched. The person saw a flash of light. The person felt something crawling on his back. These are all the kind of responses. When he poked around in this temporal lobe down in here, the people sometimes would have a vivid memory from their past. So if we were talking about learning and memory, we talk much more about this temporal lobe. But over on primary motor cortex, he would start stimulating up here towards the top. And if he shocked up here, the person's back muscle would twitch. Moved it down, the arm would twitch, the hand would twitch, a face muscle would twitch, and then maybe a tongue would twitch inside their mouth. So there was a systematic representation of the body surface here, and that's primary motor cortex. It's the part of the cortex that's closely tied to the muscles of the body. Okay? And there was a systematic representation that patient after patient, when he did this, he saw as you go from the top along the side and down the side, it went back, shoulder, arms, hands, fingers, face, tongue. And it was the same repeated pattern in every person that he did this with. You might ask where the legs are. The legs are actually dangling between your two hemispheres on the inside, and your feet are deep down in there. So primary motor cortex like this. Primary somatosensory for touch and temperature and pain is like that. In front of primary motor cortex are these other motor areas. Okay? And here's where we'll go and talk about imaging studies. We'll have time to come up and get a closer look at this after if you want. So if you can't appreciate it up on this big screen, you can come up and get a closer look when we're done. Functional imaging. Another take-home point, the brain is a biological structure. Like a muscle, if you use it, if the neurons are firing more electrical impulses, spitting out more neurotransmitters and receiving more messages, they will use more oxygen and they will need more blood flow. So, if I were to flash bright lights in your eyes, the back of your brain, the visual area of your cortex, would have more activity going on, the oxygen would get chewed up, and the blood vessels would dilate and bring more blood flow to that part of the brain compared to other parts. Okay? If you were going through and doing some sort of movement, either making a fist and releasing it, your primary motor cortex, in particular, the hand area, part down a little ways, would become more active and blood flow would increase. Functional magnetic resonance imaging is a technique that lets you measure blood flow differences in different areas of the brain. The accuracy is down to the level of maybe millimeters or so. So if there's an area of cortex, a little chunk of cortex there where the activity is picked up, functional magnetic resonance imaging will take a snapshot before you do that task, a snapshot while you're doing that task. You subtract the two images, because there's always blood flowing to your brain at all times. If there's a difference from one snapshot to the other, fMRI will show you that. So if you're just sitting here calmly, not doing anything, primary motor cortex is pretty still. Normal level of blood flow, constant flow. If I started flexing my right hand, the hand area of primary motor cortex on which side of my brain? Left side of my brain, right? Because the left side controls the right, and the right side, I don't know why that is, no one does. The left hand motor cortex would be lighting up on fMRI. So it's a very good tool because you don't have to cut open a person's head to study their brain. It's a non-invasive technique. It's a magnetic field, and when there's more or less blood, this device can pick that up. So there were a few experiments that were done, actually many experiments were done on movements. It started over a decade ago where some of the first studies came out. And yeah, if you're moving your hand, primary motor cortex lights up. But what the researchers wanted to know, Per Rowland, P-E-R, Per Rowland was the name of the researcher that did this first. He said, is there a difference between a simple repetitive movement and a complex movement where you have to follow instruction and direction? So he imaged the people when they were sitting there doing nothing. He imaged them when they were doing something very simple, like touching two fingers together. And he saw no activity in primary motor cortex, not much. And then when you started doing this, just primary motor cortex lit up because you're moving these fingers. Okay? Then he asked these individuals to follow instructions. I want you to, I'm going to count off numbers. 1, 2, 3, 4. 1, 2, 3, 4. 1, 3, 2, 4. And he would give them these instructions. So it was a difficult task. It involved listening and planning the movement. And what he saw was the area just in front of primary motor cortex. It was called supplemental motor areas, or premotor areas, were lighting up when the task was more complex. okay? Then, so we saw premotor cortex lighting up, we saw motor cortex lighting up when they were doing this. Right? So if you're just doing something simple, motor cortex alone. If you're doing something that's complicated, premotor areas and motor cortex together. Then he did the great experiment, which was say, all right, I don't want you to move your hand. I just want you to think about moving your fingers. And I'm going to tell you 1, 3, 2, 4, and give them those. So they sat there and they didn't move their fingers, but they had to think about those movements. And when they imaged their brains, motor cortex was quiet, but that premotor cortex and that supplementary motor cortex in front of it was quite active as they were thinking about these movements. Okay? So for complex movements, and I'll probably say more appropriately, movements that have not become habitual to you, movements that you have to actively think about, there's more activity in these frontal areas, the supplemental motor cortex and the premotor cortex. So that became something, sort of an interest. If someone is doing complex movements, is that really all that's required? And apparently, it's not just complexity of the movement that determines the activity in those premotor areas, but it's how much thought you have to put into that movement. And that gets us to sort of another take-home message. What is the human brain really good at? The human brain is really good at taking things that you do every day, things that you rely on, things that you have to do, and making them habits. Okay, so walking is one. Right? When you first, you can't remember when you're sort of first learning to walk, but it takes a lot of thought. You know, you're balancing, you're trying to do this, you're sort of mimicking what other people are doing, and it takes a lot of practice, and then it becomes a habit. It's something you don't even have to think about. Riding a bike might be a better example. How do you explain to somebody how to ride a bike? Well, you got to kind of push down with your right foot and then shift your weight a little bit so the bike doesn't tilt over, and then you can't really describe it that much. You just kind of get on there and you kind of mimic it and you start doing it. And at first it's a lot of thought, but then it becomes very much a habit. Okay? So the one thing I will say is that movements like tap dancing, I mean, it's just phenomenal. I can't even imagine me ever coming close to trying to learn that. I could say, well, if I wanted to, before I turn 70, do something close to that, could I do it? Oh, there's no way. But there may be a way. It could be possible with enough work and enough effort. Here's the one reason why. Okay? Just as impressive as a professional dancer is any human's ability to speak, to create words, and communicate. If you think about the coordination of motor activity, movements that you need to articulate words, it is just as impressive as hitting a home run, throwing a 100-mile-an-hour fastball, dancing. There are many muscles, including muscles pushing air through your lungs, the muscles in your vocal cords, in your throat, in your larynx, your tongue, the movements of your mouth and your lips, that all have to be coordinated perfectly. Otherwise, it doesn't sound right. So we're all experts, motor experts at speaking. Okay? So you have the ability, right? Why aren't we all expert, major league pitchers, ballroom dancers? Well, we haven't sort of put that effort into it. Speaking was important to us since we were very, very little and very, very young. We practiced it, we were motivated, and we did a lot. There's a lot of discussion. Well, you were born with it, or do you develop it? There's arguments for both. Some people seem to be born with a certain ability, but no one will argue the fact that it's approach, it's practice, it's developing expertise that really leads to becoming expert or phenomenal at something.